suppose V and W are finite dimensional, and let's say you have a vector in V, and define E as collection. It's a set of all linear maps where it kills V. Okay, it's sometimes known as the annihilator of V. Okay, so if you have the annihilator space of V, first you have to show that E is a subspace of the linear map from V to W, and part B, if V is non-zero, what is the dimension of E? That's the question. First of all, part A is quite straightforward. Proof of A is 0 times V is 0, or 0 is the zero map. It takes everything to 0. So the 0. So here 0 is the element, the 0 map here, and this 0 is the 0 element in W. Okay. So because this is true, we see that 0 is in E. So part 1 is done. Part 2, you have to show that if two maps T and S are in E, then T plus S is also in E. But see, TS in E means T of V is 0 and then S of V is 0, right? That's what it means. But then that means T plus S applied to V is TV plus SV. That's the definition of what this map is. And these are 0 plus 0, which is 0. So therefore, this is, again, in the annihilator of V. Because this map applied to V is 0. That means T plus S must be in E as well. And then 3, if T is in E and lambda is in the base field F, then T of V is 0. That's what it means here. Okay? And lambda T of V is, by definition, that's what this means, but that's lambda times 0. And any scalar times 0 is 0. So that means lambda T is in E. So we've shown that 0 is included in E, and E is also closed under vector addition and scalar multiplication, so it's a subspace. So that part is done. Now part B. Well, let me give you 2 ways to do this, and I guess the easier way to see this is just let V1 be V and extend this to a basis V1 through Vn for V. Okay. Now that means then for any T in E, T of V is 0, so T of V1 is also 0, but that's 0 W1 plus 0 W2, da da da, 0 Wm. Right, where W1 through Wm is the basis for space W, right? And then the other guys, we don't know. This could be anything. So 1, 2, W1, A, 1, M, no, sorry, A, M1, M2, Wm, da da da, TVN is A, 1N, W1, A, Mn, Wm. Okay. But now, then the matrix of T under these two bases, right, is going to be, what do we know about this matrix? You'll have some zeros somewhere, right?
Where's column?
In the first column, it'll have 0. But then now you're going to have 2, 1, no, sorry, there's 1, 2, and then A, M2, A, 1N, A, Mn. Okay? That's going to be the matrix representation. Now, furthermore, for any choice of A1, 2 through AMN, you can define T, and that's in E, right? So, furthermore, any choice of A1, 2 through AMN defines a T in E. Okay? Well, how many numbers are there? This length is N and that's M, but you're losing 1 from the N, right? Which is, so dimension of E is?
N minus 1 times N minus 1.
Yeah. N minus 1 times just M, not N minus 1, it's just that. That's the dimension, okay, yeah. You're just losing 1 column but no rows. Okay, so that's what you get, okay? So that's one way to do it. But slightly more, and I like this because it's more concrete, you can kind of see what's going on, right? Yeah, if you choose the right basis, this is what it's going to look like, and of course, if you have that, then this has to be the dimension, right? But slightly more fancy way of doing things is to take a map from, so solution 2, let F be a map from LVW to W by taking an element T and sending it to TV. Okay. So we fixed the V, and for every fixed V, this is what you get. This is a map. Okay. Now we'll have to work a little bit to show that this is indeed a linear map. Okay. So this is a vector space. That's a vector space, and you have to show that F is indeed a linear map. You'll have to work a little bit. But once that's shown, then we have the following. We have not only it's a linear map, you should also show that this is a surjective map. Okay. So show F is linear. Okay, it's straightforward. Then show F is surjective. Now, why is it surjective? TV. So, for any to show it's surjective, for any W in W, you choose anything in W, let TV equals to W. Okay? And then once again you set V1 as V, and then you just set V2 Vn as a basis. Okay? And then you define T of Vk equals to 0 if K is not 1. K greater than 1. Then what happens is that you can extend this linearly and show that with this, you can define a linear map. Okay? So you can show that this indeed is surjective. Okay, so for any W and W, you can choose a linear map so that TV equals to W. That's what I'm trying to say. Okay. So once that's proved, now you're almost done because do you know what we're going to use now? We're going to use FTLM. What's that?
Fundamental theorem of linear maps.
Linear maps, right? Which says dimension of okay, we already decided that the range of F is all of W, right? What's the dimension of this? N times M. That's what we already know, right? And what is this? Well, this by definition is E, because null space of this is what the space of math where this becomes 0. Okay. So this is the dimension of E. And the range of F is the entire W. What's the dimension of W again? It's M, right? So dimension of E is Nm minus M, which is N minus 1 times M. Okay, so that's like a fancier way of doing things. It's less intuitive. I like this explicit approach better. But you know, mathematicians like this kind of argument, like using some fancy theorems. That's all.